Hello, everybody. So I would like first to thank the organizers of NPC to give me the opportunity to present a hot topic today. Let me first share my screen. Here it is. Okay, so this subject is sustainability in HPC systems. First, let's start by a picture. So we know that digital computing now is everywhere, and this is increasing. Okay, you have a lot of IoTs, for instance, and this is visible, but you have also a big part that is completely hidden. Let's consider, for instance, this big warehouse where there are a lot of smart algorithms that are running everywhere just for distributing all the items to everyone all over the world. But besides these small devices, somehow, you have at the other side of the spectrum, big machines. So you know all, obviously, the top 500 of the largest machine all over the world. And last June, it turned that we just get the step of exaflops on a real benchmark. And this machine is called Frontier. It has more than 8 million of cores with different cores, with accelerators, and a power efficiency of 52 gigaflops per watt. If you see the picture of the top 500, Frontier is at the right side here, at the middle of this is the picture is in red. And you have the sum of all the machines just on the top of this point. And you will see here, you see here the evolution of the top 500. Okay, in green below, you have the smallest machines. So there is a big gap between the rank 500 and the first rank. But if you look at this more carefully, I just do some stats over the 10 last years, and it appeared that the performance in terms of flops has been multiplied by 32, a factor of 32, while here the average of the top 500 has been only multiplied by about 20. And if you are looking also of the top green, that shows the best machines according not to pure performance, but to efficiency, power efficiency. In the same period of 10 years, it has been multiplied by 14 for the highest one, while in average, all the machines have been multiplied by 18 only. This shows simply that performance is increasing a lot at an exponential rate, while the efficiency is also increasing, but at a smaller rate. It's like here we are running here to something, to performance only, but there is a storm here because somehow there are bad events that may come. For instance, here you can see a guy who is behaving completely like before, but in a situation, crisis situation. Okay. This is somehow a joke, but it reflects somehow the main question: could we really behave like before? I would like to address this. What's the link with HPC? You can say, okay, is the rest of this performance is based on high-tech evolution, but it's not for free. It has a big impact of the environment. If we focus on the CO2 emissions, okay, I would like first to show you how to measure all this and to really understand the hidden part of computing that is not only computing by itself. Then I will present some directions that mitigate the global warming in the field of resource management through a project that we have developed in Grenoble, and I will open discussions for further challenges at the end. This talk is divided into two parts. First part is about energy consumption challenge, and I will explain somehow the basic of this. And then I will turn to the topic of resource management. Okay, first part. Let us start by some curve here that shows the clear anthropic origin of this warming. You can see here a chart coming from the Industrial Revolution. We put the 0 here at the middle of this period. And you can see here a big acceleration. And this is here the synthesis of 4 different databases. So they all converge to a warming that is already 1.20 something degree. And actually, this is not the first part that we face this warming in the world. Yes, for sure. But here, what is very new is this big acceleration in a so short time. We had this such acceleration, but over 10,000 years. So it was very, very long time. This is not a good news. Now, let's go to some warming projection based on some analysis. I took this from Climate Action Tracker site. And the historical data on the left here are those who are that are measured. And then you have some scenarios. And you see that all scenarios will see a decreasing here in the somehow because we take some decisions to face the problem. But in the worst case, you can see that we will lead to some warming that are very, very high. And even the best scenarios here are still going to some significant warming. Okay, now how does it work? I take something out of the pure computing field. What about greenhouse gas? So you know that there exists naturally, fortunately, because otherwise you cannot have life on the Earth. Simply, it would be too cold. And but there's a big balance, a perfect balance of this that allows the temperature on Earth to be okay for life. And we know these gases. There are several, but there are 7 main gases. We know well H2O and CO2, but now also CH4, N2O, and ozone O3. And we'll focus here just on CO2, but it could have been the same on different examples here. The problem of CO2 is that it remains in the atmosphere for a very long time. So as soon as we emit something today, it stays for 1 century at least. Now, what about energy? A human, expends about 2,000 to 5,000 calories a day. This, if you want to transform this into some mechanical energy, like for cars or whatever, then it corresponds to about maximum of 500 watt per hour. And we take always the same unit, that is kilowatt per hour. Okay, it is the energy corresponding to any electrical equipment that runs for 1 hour at 1,000 watt. For instance, 1 liter of oil corresponds roughly to 10 of this unit, 10 kilowatt per hour. And the energy comes from a mix. It comes from oil here, from coal, and from wind, or from nuclear plants, okay? And any human activities require energy. And we need a lot of this with our modern lives. If you see the repartition in France, it's a bit special because we are, as you see in the chart, we are using mainly oil. This is because of the transportation and cars, a bit of coal and some gas, and a big part of electricity that mainly comes from nuclear plants. Okay, this was a rather old source, but the proportion remained about the same. If you see this repartition all over the world, you see this is completely different. The main is coal, and then oil and gas, and all the others. And you have nuclear is very, very, very small, and all renewable energy are very weak also. You can see here in this chart 2 interesting situations that during COVID pandemic, and on the top right, you have a kind of small decrease of the global energy. Okay, that is a good news from the warming. And you can see also what is the total amount here of the consumption in CO2 emissions in 1 year, about 35 to 40 billions of tons of CO2. That is a lot. Now, just look at some pictures here about increasing of population, increasing of use of water, of whatever you like, any human activity. We see that there is a big acceleration from 1950. And this is the origin of what we call Anthropocene, the new era where the activity of humans takes the lead over all the other activities. And you can see here the same kind of exponential acceleration. Now, what about coming back to the digital sector? Here is the repartition coming from our World in Data setting. You can see all domains here and all the energy spent here in term of emissions of CO2 and greenhouse gases. But you don't see any digital here. Why? Because digitally is everywhere, even in agriculture, even, okay. And then you cannot see in this chart exactly what is the part of the digital here. So what is the part of this digital? So if you see, there is some part about production or use of personal computers, networks, data centers, and into personal computers you put or even smartphones. And for data centers or HPC platform, this is our topic today, the consumption, the proportion between production and use is about 50 to 60% as far as we measured. And this is somehow, these numbers are very hard to get, but actually this is something that we know while we are speaking with our industrial partners. Now, the impact here of CO2 emission in terms of global consumed energy is about 5 to 6%. Okay, it corresponds to a bit less than 4% of the CO2 emission. That is a lot, actually. But what the main problem here is the growth of this annual growth is from 6 to 9. So this is very, very big. And now here we know that we should reduce this. We should reduce to mitigate global warming. But this sector here is in expansion. In France, it corresponds to something that is almost double from the civil aviation sector. And it is completely hidden again of any chart. Here comes a nice curve that shows somehow last year the scenario of business as usual, doing like it is. It will still grow at a rate of 9%. But there are different scenarios here that are even worse. So we are really to take care. I will come back to this chart just after. Now, I will present two things here that are very important to understand how does it work and what could be our measure in order to put some leverage mechanism to mitigate the CO2 emission. There are LCA, life cycle analysis, and rebound effects. So let's start by LCA. LCA, for any production of digital component here, we start by extracting something, and for extracting for mines, for big mines here, and it costs a lot of CO2 emission also, obviously. After this, we have the fabrication of the component in some big companies, and then transportation. Obviously, there are some transportation also from mine to the fabrication, but okay, I will isolate this step separately. And at some point, then there is the data center, the new HPC system that is deployed, and you can run here. This is an example of a run of a weather forecast, for instance. And then, as after 4 to 5 years, all the computers become a bit old, and then we may or not use them for another topic or refresh them, or we can have the end of life of this component. This is the whole steps of the life cycle analysis here. And you see that usage here is only at the bottom, is only a part of this whole system. What now is rebound effect? Rebound effect here is, let's consider, this is a kind of abstract presentation, but I think you will get it. Let's consider any material resource that could be CPU, it could be energy, whatever, okay? And imagine a set of users that are using this energy, and they are consuming the whole resource, okay, at some point. And now comes a kind of technical improvement. And within this technical improvement, people are able to do the same, but in a much, much smaller use of the same energy. So here, in my picture, you see that there are some idle resources here. If we stay as we were before the technical improvement. But this idle, what to do with this idle stuff? We could save it completely to mitigate climate, or the same users can be a bit more, can do a bit more. This is always what we remarked. Okay, we are asking more because there are some available resources. We are using more, and at some point, if we are using more and again, there is what we call the backfire. This is the moment where the new technology that is deployed allows much more people to use this resource as before. And the global thing is that at the end, you will use more resources than before the improvement. This is what we call Jevons effect or rebound effect with the phenomenon of backfire. And there is something even worse, that all these resources that are freed, that are idle, could be used by something else because they are available somehow. And this is what we call an indirect effect, second order rebound effect. Okay. Now, what is the problem with life cycle analysis? Because people usually did not go to these measurements. Why? Because it's very difficult. First, there is limited available of stats, and the data are not public. They are usually with the admin of the HPC system, and they don't want to be shared. And all the life cycle analysis are biased because if we ask our colleagues of in company of constructors, they are far too optimistic actually. And okay, another fact also that makes it very difficult to estimate is that it takes time to establish a full life cycle analysis. We try to do this in my group for several components, but it's a very long time. It needs 1, 2 years or more. And if you are comparing this to the lifespan of the machines, of the smartphones, for instance, this is too long, and to provide the data, and the digital component are already in the next generation. Another problem is the systemic effect that is very complex and so on. What's the takeaway message of this presentation of LCA and rebound effect? That most climate impact analysis, that there are some, but they are only restricted to usage phase of the LCA and not to the whole effect that should be done. Coming back to HPC now and Frontier, if you are looking for Frontier, Frontier has been deployed in Tennessee, so it's used in Tennessee. Tennessee is on a good year. You have the mix, the energy mix of the US. You guess that this is the US map. And actually, the darker is the more carbon intensive it is. So here, Tennessee is not a so bad state for this point of view. And actually, here, if you see exactly the distribution on Tennessee Valley here, these are the data that are available. I just look at some adequate website in the US, and you can see here that there are a lot of nuclear plants here. You have a bit of coal, a bit more gas, and all to all, and renewable is only 3%. So it's a reasonable one. It does not use a too bad energy, too carbon intense energy, but it requires 52 gigaflops per watt. Okay, and it consumes 21 megawatt. This corresponds roughly to one round trip Paris-New York per hour. This is a lot, just for usage of this machine. And again, no data about the phases out of the usage are provided here, and no news also about rebound effect. It's like you have the full LCA here, and that all these phases are completely forgotten here, and you just focus on a small part of the life cycle analysis here. And for this part, then we can have some informations and try to improve this part. But all parts should be also improved. Okay, now a second takeaway message here is that we behave as scientists like the energy is completely cheap and infinite, but this is no more true. What we really have to face is think about our algorithms into a term of finite resources. Now, let me add another curve into the previous chart. This is the curve here below from 2019 here. It's what we should do is to keep a trajectory that is the same as before. We had a big improvements here in our systems. We should be able to behave within these finite resources, at least not to increase the use of the energy for running our algorithms. Okay, this is the last slide of my presentation. I will now turn to a more specific topic on resource management.